In this video, we will move from comparing groups with A/B testing to predicting outcomes with linear regression. Our goal is to understand how changes in marketing inputs, such as advertising budgets, are related to changes in performance, such as sales. We will start with a simple model using one variable, then expand to a multiple regression model with several channels. Along the way, we will learn how to read coefficients, interpret R-squared, and check whether the model makes basic sense using residuals. By the end of this video, you should be able to use linear regression as a practical tool to support marketing decisions and be ready to extend these ideas to logistic regression and other machine learning models. Regression is a statistical technique that helps us model the relationship between an outcome, which we call the dependent variable, and one or more predictors, which we call independent variables. In marketing, the outcome might be sales or conversion rate, and the predictors might be things like ad spend, price, or store size. There are three main purposes of regression. First, describe. We use regression to summarize and explain how variables move together. For example, how income is related to reported happiness in the plot on the right. Second, control. Regression lets us adjust for other factors so we can isolate the effect of one variable while holding others constant. Third, predict. Once we have a model, we can forecast future outcomes using known inputs. We will focus on two basic types. Simple linear regression uses one independent variable to predict the outcome. Multiple linear regression uses several predictors at the same time. The rest of this video will walk through both types and show how to interpret them in a marketing context. Now let's switch into Python and look at a real dataset. We will use the classic advertising and sales dataset. Each row is one market, and we have 4 columns: TV advertising budget, radio budget, newspaper budget, and the resulting product sales, all measured in thousands. Our goal for the rest of this notebook is to predict sales from these 3 ad channels. In this first step, I load the data, check the shape, and print the first few rows so you can see what it looks like. Then I show basic summary statistics, such as the mean and standard deviation for each variable. Finally, I draw simple scatter plots of sales against TV, radio, and newspaper. Take a look at the patterns. TV and radio already look roughly linear with sales, while newspaper seems much weaker. This quick exploration motivates why linear regression is a reasonable tool here and what we might expect from the models we build next. Now, we focus on the key pieces that go into a regression model. First, we have the dependent variable, y. This is the outcome we care about and want to predict or explain, such as sales, click-through rate, or customer satisfaction. Next, we have the independent variable, x. This is the predictor we think helps explain y, for example, TV advertising spend or price. In a simple linear regression, we connect x and y with a straight line written as e equals b0 plus b1 times x plus e. Here, b0 is the intercept. It is the value of y when x is 0, the point where the line crosses the vertical axis. b1 is the slope. It tells us how much y is expected to change when x increases by 1 unit. This is usually the number we care about most in marketing. Finally, e is the error term. It captures everything that affects y but is not included in x, as you can see by the vertical gaps between the blue dots and the red line in the picture. In the next steps, we will estimate b0 and b1 from data and interpret what they mean in a marketing context. Simple linear regression is the simplest version of the idea we have been building. We focus on one predictor, x, and one outcome, y, and we fit a straight line that captures their relationship. The goal is to find the best fitting line so that when we plug in a value of x, the model gives a reasonable prediction for y. Think about price and demand. Let X be the product price and let Y be sales or demand. As price increases, sales usually decrease. Simple linear regression lets us quantify that pattern. The slope of the line tells us on average how much sales change when price goes up by 1 unit. In other words, it answers a practical question for managers. If we raise the price, how do sales numbers typically respond? Now, we build our first regression model using only the TV budget. Here I take the TV column as X and sales as Y, then split the data into a training set and a test set. The model learns the line from the training data and we check how well it predicts sales in the test data. The scatter plot shows the actual test points as dots and the fitted regression line as a smooth curve. This is our simple linear regression, sales as a function of TV spending. Below the plot, you see 3 key numbers. The intercept is the predicted sales when TV spending is 0. The slope tells us how much sales are expected to increase when TV budget increases by $1,000 on average. Or squared shows how much of the variation in sales is explained by TV alone. Keep an eye on that R squared value because in the next part we will add radio and newspaper and see how much the model improves. Now we need a rule for choosing which line is the best one. Ordinary least squares or OLS is the most common rule. For each data point, we look at the vertical distance between the actual value and the value on the regression line. That distance is the error or residual. OLS squares all of these distances and adds them up. The best line is the one that makes this total squared error as small as possible. Another way to think about it is in terms of variation. The total variation in Y can be split into 2 parts. The part explained by the line and the part the line cannot explain. OLS chooses the line that maximizes the explained part and minimizes the unexplained part. This is what our software is doing for us when we fit a regression model. Next, I extend the model to use all 3 ad channels at the same time. Here, TV, radio, and newspaper become the predictors, and sales is still the outcome. I split the data again into training and test sets, fit a multiple linear regression model, and then predict sales for the test set. Look at the evaluation numbers. R squared is now much higher and the mean squared error is lower than in the TV-only model. That means the 3-channel model explains more of the variation in sales and makes more accurate predictions. Adjusted R squared is close to R squared, which tells us that adding these predictors is genuinely improving the model rather than just inflating the metric. Below, you can see the intercept and the coefficients for each channel. Each coefficient shows the expected change in sales in 1,000 units when that ad budget increases by $1,000, holding the other channels fixed. Comparing these values gives a first sense of which channels are most effective in this dataset. Once we have a regression line, the next question is whether the relationships we see are real or just noise. That is what hypothesis testing in regression is for. For each coefficient, we start with a null hypothesis that the true coefficient is 0, meaning this x has no linear relationship with y. The alternative hypothesis is that the coefficient is not 0, so changes in x are associated with changes in y. Software reports a t-test and a p-value for each coefficient. If the p-value is below a chosen cutoff, such as 0.05, we reject the null hypothesis and say that this variable significantly contributes to explaining y. There is also an overall f-test for the whole model. A significant f-test tells us that at least one predictor in the model has a non-zero effect, so the regression fits better than a model with no predictors at all. Now that we have a multiple regression model, we should check whether it behaves reasonably. In this step, I compute the residuals, which are simply actual sales minus predicted sales for each test point. Then I plot these residuals on the vertical axis against the predicted values on the horizontal axis. The dashed horizontal line at 0 represents perfect prediction, What we want to see is a cloud of points scattered randomly around zero, with no strong curve and no clear funnel shape. That pattern suggests that a straight line model with roughly constant variance is a reasonable approximation. If we saw a strong curve, we would worry about nonlinearity, and if we saw a funnel pattern, we would worry about changing variance. Here, the residuals look fairly random around zero, so together with the R-squared numbers, this gives us a quick practical check that the linear regression model is good enough for basic prediction in this dataset. Linear regression is powerful because it turns historical data into predictions. Firms use it to forecast sales, stock prices, customer behavior, or demand for a product, and those predictions support decisions such as budgeting, targeting, or capacity planning. By modeling the relationship between inputs and outcomes, managers can run what-if scenarios instead of guessing. At the same time, regression shows correlation, not automatic causation. A classic example is ice cream sales and temperature. They move together, but ice cream does not cause hot weather. In marketing, a strong coefficient on ad spend does not prove the ad alone caused the outcome. There may be other factors in the background. So results must be interpreted carefully, especially for policy or strategic decisions. You will see regression across many domains. In business, it links advertising budgets and sales to optimize marketing strategies. In healthcare, it relates patient characteristics to health outcomes to assess risk. In environmental studies, it connects pollution levels to industrial activity and weather patterns. The same tool with different variables helps answer concrete questions in each field. To wrap up the modeling part, I now compare the TV-only model with the 3-channel model side by side. The table shows R-squared and mean-squared error for both. The TV-only model already captures a decent amount of variation in sales, but once we add radio and newspaper, R-squared clearly increases and MSE goes down. That tells us the multiple regression model fits the data better and gives more accurate predictions, which is what we want for decision making. Next, I use the multiple regression model in a simple what-if scenario. I plug in a hypothetical campaign plan, for example, $100,000 on TV, 20 on radio, and 10 on newspaper. The model returns a predicted sales value in 1,000 units. This is exactly how linear regression is used in practice, not just to describe relationships, but to support planning. A manager can adjust the ad budgets, see how the predicted sales move, and use that as one input when choosing between alternative media mix strategies. Linear regression is useful, but it is not a magic hammer for every problem. First, it assumes a straight line relationship between the predictors and the outcome. If the true pattern is strongly curved or changes across ranges of X, a simple linear model can miss important structure. Second, the fitted line can be very sensitive to outliers. A few extreme points, such as one campaign with an unusually high spend and noisy results, can pull the line up or down and distort the estimated effects. Third, linear regression is designed for continuous dependent variables. It is not appropriate when the outcome is categorical, for example, purchase versus no purchase, churn versus stay, or click versus no click. For those binary outcomes, we use a different but related tool, logistic regression. Choosing the right model always depends on the data structure and the type of outcome you have. Understanding these limitations helps you know when linear regression is good enough and when you should switch to another model. Linear regression already lives in the same world as machine learning. Both try to predict outcomes and recognize patterns in data, and both are trained by feeding in historical examples and adjusting parameters to match what actually happened. The training rule is also the same idea you see in many ML models. Choose the parameters that minimize some loss, such as the sum of squared errors. More complex algorithms change the loss function and the model shape, but the optimization logic is very similar. We then evaluate models using metrics like R2 or accuracy and by checking performance on new data, just as we do in machine learning with validation and test sets. Because of this, linear regression is often viewed as a foundational supervised learning algorithm. In the next step, we will build on the same ideas to study logistic regression, which is used when the outcome is binary, such as purchase versus no purchase. In this video, you have seen how linear regression turns data into a simple, usable model for marketing decisions. We started from the advertising dataset, explored the relationships between ad budgets and sales, then built a simple regression using TV only and a multiple regression using TV, radio, and newspaper together. You learned how to read the intercept and slopes as expected changes in sales when each channel's budget increases, how to use R-squared and mean-squared error to compare models, and how a quick residual plot helps you check whether the linear model looks reasonable. Finally, we used the fitted model in a what-if scenario to predict sales for a new campaign plan, just like a manager would do in practice. Going forward, we will extend the same ideas to outcomes that are not continuous. When the target is binary, such as purchase versus no purchase, click versus no click, we switch from linear regression to logistic regression. The core logic is similar, but the model outputs probabilities instead of raw numbers and uses a different link function.